Let's say you have a pile of papers with names on them, and you need to order them alphabetically by name. One way to sort them would be to look through the papers and find a paper with a name that should be alphabetically first, such as Aaron. We then look for the next name, for example, Anna, which we add behind Aaron into our new sorted pile. We continue looking and adding names one by one to the sorted pile until we sort everything. The problem with this approach is that looking for each name can take a long time, as you have to look through every paper to find the alphabetically next one. This way of sorting is called selection sort, and although it's simple, it doesn't scale well. Imagine if instead of 8 papers, we had a 1000. It would take forever just to add one paper, as there would be so much we'd have to look through. Another possible way of sorting them would be to take the top paper from our pile and shuffling it into its proper place. So, for example, we take our first paper here by John and throw it into our new pile. We then add Chris's paper and shuffle it into place, going before John alphabetically. We continue taking papers from our original pile and we insert them into their alphabetical order in the new pile. This way of sorting is called insertion sort, and it also faces scalability problems. The more papers there are, the harder it becomes to place every paper in the correct order. Notice how I had to shift all these papers just to add Bill's paper into the right spot. While these solutions work, they can become ridiculously time-consuming, even for computers to do, if we have to sort thousands or millions of papers. This is where merge sort comes in, a more efficient way of sorting anything. So here I have 2 piles of papers. If I wanted to combine these piles into one big sorted list, I would have to look through every paper to find first Alan, and then Austin, and then Bertha, and etc. It would actually be no different from having one big unorganized pile that needs to be sorted, so it doesn't help us. However, if these 2 piles are already sorted beforehand, as I just did on the screen, merging them together becomes simple. Let's say pile 1 has papers by Alan, Bertha, Don, and Mark, sorted alphabetically by name. Pile 2 has papers by Austin, Kat, Fred, and Gordon, also sorted alphabetically by name. Now, because they are sorted, instead of having to look through everything, we can actually just compare the first paper from each pile. So if we compare the first papers of our piles, Alan and Austin, Alan comes before Austin alphabetically, so we take Alan's paper as the first one. Now we compare Bertha, the new first paper of our first pile, and Austin, who is still the first paper in our second pile. Austin comes before Bertha alphabetically, so it will be the next paper. We then continue comparing the first paper from each pile. So Kat versus Don, Kat is first alphabetically, and then Don and Fred, Don is first, and then we end with Fred, Gordon, and Mark in that order. Our end result is one big sorted pile that was easy to achieve, just because the 2 piles we were merging together were already sorted themselves. This method of fusing 2 sorted lists together is how merge sort works its magic. So here we have 8 papers with names on them that we want to sort alphabetically using merge sort. First, merge sort will take all your data, these papers containing names at the top here, in our case, and split it in half into 2 piles. We then split again and again and again until we reach individual groups of 1 paper each. If you think about it, there are now 8 sorted piles of papers. Next, merge sort will take pairs of these named papers, like Michael and Franklin, and merge them into ordered groups of 2. Here it's easy, as each pile has only 1 paper, so we only need to compare 2 names to get our new sorted lists. So first we'll merge the pile containing Michael's paper and the pile containing Franklin's paper. Franklin comes before Michael alphabetically, so we flip them around and create a new group containing Franklin and Michael, sorted in order. We do the same for Monica and Zeus, Trevor and Barney, and then Alfred and Millicent. Merge sort essentially divides everything and then slowly builds it back up again in order. And at this point, we now have 4 piles of 2 papers each, and most importantly, each pile is sorted. Next, we merge these piles again. If we want to combine Franklin's pile and Monica's pile, we compare the first paper in each pile. Franklin comes before Monica, so we add it to the front of our new merged pile. Next, we compare Michael and Monica. Michael comes first, so we add Michael next. Our first pile is gone, so there's nothing to compare Monica to, so we just stick it to the end of our new pile. Same for Zeus. Now let's merge the other 2 piles. First, we compare Barney and Alfred. Alfred is first. Compare Barney and Millicent. Barney is next. Compare Trevor and Millicent. Millicent is next. And Trevor is the last name, so simply add it on to the end. And notice what we have here. 2 lists, each sorted, that we want to merge together into one big sorted list. We have 1 more merge left until we get our end result, and it will go just like the example I showed 2 minutes into this video. So as usual, we compare the first paper from each pile and pick out the alphabetically first one. Then rinse and repeat. So let's compare the top papers. Alfred first, then Barney before Franklin, and then Franklin before Millicent, Michael before Millicent, Millicent before Monica, Monica before Trevor, and then Trevor before Zeus, and lastly add Zeus to the end. We've now recombined all our piles back together and achieved our one sorted group of papers. While merge sort might look like a lot of work, it is incredibly efficient and scales well. Merge sort's runtime is n times the logarithm of n, which simply means that if n represents how many things we're sorting, like papers, then n times log of n is how many steps it will take to sort. So if we were sorting 1 million papers, merge sort will take 1 million times the logarithm of 1 million steps to complete, which is about 20 million steps. To compare, the first 2 ways of sorting I showed at the beginning have a runtime of n times n, or n squared. So if we were sorting 1 million papers using one of those methods, it would take 1 million times 1 million steps, aka 1 trillion steps to complete. Merge sort is one of the best sorting algorithms out there, and it is used often in programming and computer science. Thanks.